Hi, my name is Justine Harkness, and in this video, we'll look at how to predict how changing the concentration of a reactant will affect the rate of a reaction. The overall order of a reaction is equal to the sum of the exponents in that rate law. Now, there are a few common orders that you'll see, and those are zero order, first order, and second order. So let's start by looking at a zero order reaction. Now, in zero order reactions, the rate of the reaction is completely independent of the concentrations of the reactants, meaning that any change I make to reactant concentration has absolutely zero effect on the rate of the reaction. And we can determine a lot about a reaction order based on the rate constant itself. Now, if we were to look at this rate law, the rate will always have units of molarity over seconds. And in this rate law, notice that we have each of our reactants to the zero power, and any number raised to the zero power is 1. So the rate law is just k times 1 times 1, which is just k. So we can do a little unit analysis here, where the rate, which we've already said is molarity per second, is equal to the rate constant, and then we don't have anything else here because all of our other numbers here are just 1. So in a zero order reaction, the rate constant is just molarity over seconds. We actually see a lot of applications of zero order reactions to biology. One that you may or may not be familiar with is the processing of alcohol by the human liver. So the human liver can only process 1 alcoholic drink per hour, and it doesn't matter how much alcohol is in the system. It's always that same 1 drink per hour. The rate is independent of the concentration, again, indicative of a zero order reaction. Our next order is a first order reaction, and these have a rate that is directly proportional to the concentration of just 1 reactant. So any change in concentration would literally correspond to a change in the rate. So if I were to double the concentration of reactant, that would also double the rate of the reaction. And we also see different units for that rate constant. So if we look at the rate, which is always in molarity per second, we would have just molarity, since we only have 1 reactant raised to the first power. And in order to get molarity per second as our rate constant would need to have the units of 1 over second, which you'll also sometimes see as just second to the negative 1. First order reactions are fairly common. One great example of this would be carbon dating. Radioactive decay will always follow a first order reaction. So we can actually determine how old things are based on the different isotopes of carbon in a material. Our last order is a second order reaction, and these ones are a little bit more complicated. Remember, the order of the reaction is equal to the sum of the exponents in a rate law. A second order reaction could have 1 of each reactant, so you'd have 1 and 1 to give you 2 as your overall order. Or you could see 2 of the same reactant. The rate constant, of course, will also be different. Remember, rate is still molarity over second. Here, since we have 2 reactants, we would have molarity squared. And in order to get molarity per second as our rate, the rate constant would need to be 1 over molarity in seconds, which you can also see as molarity to the negative 1, second to the negative 1. So now let's apply this content to a practice question. So here we are given a balanced chemical reaction, which we pretty much will ignore because remember, the balanced chemical reaction tells us nothing about the rate of the reaction. So this is where we need to focus, the rate. Now, interestingly enough, this is a third order overall reaction, and these are pretty rare in chemistry, since that means you need to have 3 different molecules at the right time, the right place, and the right orientation to react. So let's look at how changing the concentrations of each of these reactants will change the rate of the reaction. Now, if we were to look at NO, in our rate law equation, it has an exponent of 2, indicating that this is a second order reaction, at least in regards to NO concentration. So if we were to double the concentration of NO, that would lead to a 4-fold increase in the rate of the reaction. Now let's turn our attention to oxygen. In our rate law, oxygen has an implied exponent of 1, indicating that for this reaction, it is first order in regards to oxygen concentration. So any increase in oxygen concentration would have a linear increase in the rate. So if we were to double the concentration of oxygen, that would give us a 2-fold increase in the overall rate of the reaction. So now you should feel more comfortable determining how changes in reactant concentration will affect the rate of a reaction.